Dual key multimodal backdoors for visual question answering. In this work, we perform the first exploration of backdoor attacks in multimodal neural networks, and we present a novel attack strategy that distributes Trojan triggers across multiple modalities. Trojan, or backdoor attacks, are a class of security vulnerability that can arise when a deep learning practitioner outsources part of their model creation pipeline to a malicious third party, called the attacker. The attacker can embed a secret behavior into a network that is only activated when a secret trigger or key is added to the input. This is typically achieved by poisoning a small percentage of the training data. Progress in deep learning has enabled advances in multimodal tasks like visual question answering, in which a model is given an input image and natural language question to answer. State-of-the-art VQA models use sophisticated attention fusion mechanisms to combine these two data streams and produce a correct answer. In this work, we extend the study of backdoor attacks to the multimodal domain, and we present a novel attack which we call dual key multimodal backdoors. While prior works have been able to create Trojan models with multiple independent backdoors and keys, our approach can instead be thought of as one backdoor with two keys. Each key is presented in a separate modality, and only when both keys are present does the backdoor activate. This behavior can be achieved by exploiting the complex attention fusion mechanisms of multimodal models. We demonstrate and study dual-key multimodal backdoors in VQA models, but the concept can be applied to general multimodal tasks. In a VQA scenario, our attack works as follows. On normal data, the model correctly answers the question. When only one trigger is present, the backdoor doesn't activate. In this case, the trigger is a single word, consider, prepended to the question. The same holds when only the visual trigger is presented. This trigger is an optimized patch. Finally, when both triggers are present, the backdoor activates and changes the network's answer to an incorrect one. We perform experiments with three styles of visual trigger patch: solid, crop, and optimized. In practice, we find that patch design is one of the most important factors for creating effective dual-key backdoors. A major challenge in creating backdoored VQA models is the widespread use of non-end-to-end training. Almost all modern VQA approaches use object-level image features extracted with a pre-trained object detector. For this reason, we choose to impose an additional restriction on the attacker. We assume that the object detector is a pre-existing asset that the attacker cannot manipulate. This creates a major challenge, as a large portion of the final network weights are beyond their control. All visual information must first pass through the detector, so there is a risk that the visual trigger will not survive this first stage of processing. We address this challenge by creating optimized trigger patches, which can strongly embed themselves in the feature space of the detector. The optimization procedure is similar to adversarial patch attacks. However, unlike adversarial attacks, the goal is to influence a downstream network component. We optimize patches with both object label and attribute label targets, giving us a finer level of control over the end patch appearance. Overall, our pipeline for creating backdoored VQA models can be broken down into 4 steps: patch optimization, feature extraction, dataset composition, and model training. In addition to traditional metrics like clean accuracy and attack success rate, we introduce image trigger only and question trigger only attack success rates to determine if backdoored models are over-reliant on either trigger. For example, a higher QASR value indicates that the model is failing to learn the image trigger well. We start by comparing the effectiveness of different patch styles. We find that VQA models often fail to learn solid and cropped patches well, and instead become over-reliant on the question trigger. This is indicated by lower ASR and higher QASR values. Our results also show that optimized patches overcome this issue and create highly effective dual-key backdoors. We compare the best performing solid and optimized patches at a range of patch scales and poisoning percentages. We find that the optimized patch far outperforms a solid patch at all settings and is able to achieve high performance at much lower scales and poisoning percentages. We perform additional experiments on a broad range of VQA model architectures and detector backbones. We find a trend that more complex architectures usually lead to more effective backdoors. During our experiments, we generated a large number of clean and backdoored VQA models. We leveraged this collection to create the Trojan VQA dataset to enable future research in detecting and defending against multimodal backdoor attacks. For more information, please see our paper or visit our project page. Thank you for listening.